Hello there. Thanks for joining us again in the happiness room. I know this is the happiness room and all, but the real world is not all about the happy path. We have to deal with nasty things like exceptions and concurrency. Thankfully, our speaker for this session, Gromakovskii, a team lead and Haskell developer with nearly 6 years of experience at Zerocell, is here to teach us all about how to deal with that in Haskell. Ivan tells me that he's open to questions in the middle of the talk, but if there's not enough time, let's take the questions to the Q&A room. All right, over to you, Ivan.
Hello, everyone. Thank you for attending my talk. The topic is exceptions and concurrency. So it consists of 3 parts. And in the first part, we will talk about the basics of the exception machinery in Haskell. So an exception in Haskell is just a value of any type that is an instance of the exception type class. And in order to introduce this type class, we also need to introduce the SomeAsyncException data type. It uses existential quantification. So this definition may look a bit scary to you, but basically it's a data type with one constructor called SomeAsyncException that holds a single value of type X. That can be of any type, so it uses for all quantifier, and all we know is that it's an instance of exception. And if we look at the exception type class, we will see that it has 2 constraints, typeable and show. And the show constraint is needed to be able to print exceptions. Without it, the runtime system would be unable to print uncaught exceptions, for example. You may notice that it also has display exception method, so it may look redundant. But this method was added much later than the type class itself, and we will not discuss it in this presentation. And the typeable constraint allows us to get runtime representation of a type in runtime and to check if 2 types are equal. So apart from that, there are 2 methods, toException and fromException, that allow us to convert to and from SomeAsyncException data type. By default, these methods are implemented this way. So toException simply applies SomeAsyncException constructor, and fromException extracts a value X from SomeAsyncException. This value is bound here. The type of this value is bound here. So it may be different from E. That's why we are using cast function from the typeable class, which returns just this value if X is the same time as E, and nothing if the type is different. So now you may wonder why we may need to define different definitions for this method. The reason is that it allows us to create a hierarchy of exceptions, similar to how inheritance works in object-oriented programming. So on this slide, the code is copied from the base package. It defines some async exception data type, which has the definition exactly the same as SomeAsyncException, except for the name. Its exception instance uses default method definitions, so this type is a child of the SomeAsyncException type in the hierarchy of exception. And additionally, there are 2 functions, and on the next slide, we will see how they are used. So there are 2 data types, async exception and allocation limit exceeded, that we want to be children of the SomeAsyncException type. And SomeAsyncException type is semantically a parent type for all asynchronous exceptions. In exception instance definition, we use functions from the previous slide, async exception toException and async exception fromException. Now let's see what will happen if we specialize toException method for async exception data type. So we will inline this definition to toException dot SomeAsyncException, and toException is applied to a value of SomeAsyncException type, which uses default exception instance definition. So it will simply apply SomeAsyncException constructor. So toException for async exception type applies to constructors. Now, if we look at fromException, we will again inline this definition. So it extracts SomeAsyncException, firstly, using default definition, which just extracts from SomeAsyncException and uses cast. And then it extracts value from SomeAsyncException and returns cast A. So if A is has the type async exception, it will return just value. And if not, the conversion will fail and return nothing. So this way we have built a simple hierarchy of exception types. The base type is SomeException. It has a child called SomeAsyncException, and it has two children, allocation limit exceeded and async exception. It's similar to how we would do it in imperative languages. For example, in Python and C++, we would use normal inheritance to achieve the same. Now let's see what functions we have in Haskell to work with exceptions. There are three groups of functions: throw functions to throw exceptions, functions to catch exceptions, and functions to deal with resources. Throw and throw_to functions will be discussed a bit later. And throw_io function has the following type. It takes any exception value and returns io_a, where a can be arbitrary because it doesn't really return any value of type a. And for catching, the two primary functions are catch and try. The first one takes a callback, which is executed in case of exception. And the second one returns either exception or the value if there was no exception. They can be quite easily implemented in terms of each other. And the bracket function allows us to allocate some resource, release this resource when we don't need it anymore, and to do something with this resource. And it guarantees that the resource will be released regardless of what happens during the execution. There are other versions of these functions, so they are similar but have slightly different types, and sometimes they are more convenient to use. Now we can see why we need to be able to cast exceptions. So at the low level, there are raise, io sharp, and catch sharp primitives that work with some exception type. However, we want throw, io, and catch functions to work with any exception value, so to be polymorphic in type E. So to work with these primitives, we need to be able to convert to and from some exception. In throw_io, we use to exception to get some exception value. And in catch, we create a handler that takes some exception, and we use from exception function to convert it to the desired type, to this E type. If conversion succeeds, we use handler pass to the catch function. And if it doesn't, then we simply rethrow the exception. Now let's imagine that we want to catch some async exception. Intuitively, it should catch a value of some async exception type and of any children type in the hierarchy of exceptions. So let's see what happens when we throw an exception of type async exception. It will use to exception method, and as we have seen before, it applies two constructors: some async exception firstly, and then some exception. Now, when we catch it as some async exception, it will unwrap, it will use from exception to unwrap it from some exception, and it will produce this some async exception, which stores E. If we were using catch with type parameter async exception, we would additionally extract this E from some async exception. So it works if we catch some async exception or if we catch async exception directly. This approach is described in more detail in the paper An Extensible Dynamically Typed Hierarchy of Exceptions. So who are interested in this topic, I recommend reading this paper. As we have seen, working with exceptions in Haskell so far was quite similar to working with them in imperative languages. So here we compare Haskell with Python and C++. So we can create a hierarchy of exceptions, we can throw them, catch them, and we have a method to work with resources and safely acquire and release them. But there are two kinds of exceptions in Haskell that are somewhat unique and unusual. The first kind of such exceptions is exceptions in pure code. By pure code here, I mean that they can be thrown outside of the IO monad. The primary way to do it is to use the throw function, whose type is very similar to throw_io, except that it returns A, which is not necessarily IO. This function is rarely used itself, but there are two more often use functions throw and undefined, error and undefined. Error use throw internally, and undefined uses error with a specific string. Another function which is relevant here is called evaluate. So it takes a value a, and it returns IO that may throw an exception if a holds an exception. So if throw was used to produce a. Now you may wonder why we can throw an exception in pure code without doing IO, but the only way to check whether there was an exception is to use evaluate, which returns IO. And can we have, for example, evaluate pure function which takes a and returns either some exception if there was an exception in evaluating it, or returns the value of a without any exceptions. It turns out that in theory it's possible, but there is a good reason why it's not done this way. So let's look at X definition on this slide. It sums two values, and both of them produce an exception. The left argument produces division by zero exception, and the second argument produces error call exception. In Haskell, the evaluation order of arguments is not specified, and it allows the compiler to make certain optimizations. We can specify the evaluation order, and then the result of X will be deterministic, but it would disable some compiler optimization, and it's not the price that we want to pay. So since the order is not specified, we can't be sure that this expression will always return true. It may evaluate X as divide by zero, and then it may evaluate it as just error. That's why evaluate returns IO, and its semantic is that it returns any of the exceptions that was produced while evaluating X. This approach is called imprecise exceptions, and it's described in detail in the paper Semantics for Imprecise Exceptions. The second part is about asynchronous exceptions, which are another kind of unusual exceptions present in Haskell. So asynchronous exceptions differ from synchronous exceptions in the way they are thrown. They happen externally to the current thread. So the primary source of asynchronous exceptions is the throw2 function, which has the type similar to throw IO, but it takes an additional argument of type thread ID, and it throws exception to a thread with this ID. Another possible source of asynchronous exception is the runtime system itself. So it may throw, for example, stack overflow, heap overflow, and user interrupt exceptions. The tricky thing about asynchronous exceptions is that they can happen in any IO action. So even if you are sure that you are running IO action that doesn't throw any exception, you still can't be sure that it won't be interrupted by an exception because it may be thrown asynchronously. There are two good examples which rely on asynchronous exceptions and use them under the hood. The first one is with async function from the async package. It takes IOA action and runs it in a child thread. So it creates a new thread to run this action. And it takes another action which has async A parameter. This async A is a handle for this thread, and it runs IOB action in the current thread. So it guarantees that whenever the parent action, this action stops, the child action will be stopped before this async returns. So the child thread can't be left running. And timeout function guarantees that IOA action won't be executed for more than given amount of microseconds. Both these functions run another thread under the hood, and they use asynchronous exceptions to let one thread kill another one. Sometimes it's not desirable to let asynchronous exceptions happen in any point in the program. That's why exceptions can be masked. There are three masking states in which your program can be. By default, the program is in unmasked state, in which asynchronous exceptions work normally, so they can happen in any point in the program. And there are two masked states. The first one is masked interruptible state. So in this state, asynchronous exceptions can't happen in an arbitrary place, but they are still possible in interruptible operations. So this masked state tries to kill two birds with one stone. On the one hand, it blocks asynchronous exceptions, but on the other hand, they are still possible to stop blocking operations. So an example of blocking operation, interruptible operation, is take mvar function, which may block if mvar is empty. And the third masked state is masked uninterruptible. In this state, no asynchronous exceptions are possible. They are completely blocked. So the reason why this state exists is to prevent deadlock, for example, by being able to kill the thread that is stuck waiting for something. Masking exceptions is quite intimidating topic, particularly because there are two masked states, and because it's quite hard to determine whether some library function calls an interruptible operation or not. So the documentation for control exception package only provides a list of operations guaranteed not to be interruptible, but you can not reliably know whether some function that does some magic inside is interruptible or not. The use case for exception masking is the bracket function. So if you call bracket and pass acquire, release, and action arguments, it will run acquire and release inside masked uninterruptible state, and action will run in the state inherited from the place where bracket was called. So normally bracket will be called in unmasked state, and the action will run in unmasked state as well. But if you call bracket inside, for example, masked interruptible state, then action will run in masked interruptible state as well. So it will not automatically unmask exceptions. However, we shouldn't mask exceptions too often, because when we run in masked state, functions from the previous slide will not work, so they will not be able to throw asynchronous exceptions until we stop blocking them. Asynchronous exceptions are described in detail in the paper Asynchronous Exceptions in Haskell. In particular, you can read more about exception masking and motivation for this design. So exceptions in Haskell, and especially asynchronous exception, are quite easy to misuse. And if you make a mistake, it may be quite hard to debug. So there needs to be some set of guidelines for working with them. And there is a package called Safe Exceptions with really great documentation, which not only covers the package itself, but it also describes some mistakes that can be made and how to avoid them. So I don't want to repeat it here. I just recommend reading this README, even if you don't intend to use this package. So there are two primary differences from functions from base in this package that I want to highlight here. Most importantly, it prevents you from swallowing asynchronous exceptions, where by swallowing, I mean that you catch an asynchronous exception and do not rethrow it. This is bad because, for example, it breaks timeout and with async functions, which rely on being able to deliver asynchronous exceptions. And secondly, bracket from Safe Exceptions uses masked uninterruptible state for cleanup action, unlike bracket in base, which uses masked interruptible. That will rarely be noticed by you, but I didn't find it in documentation, and I was confused by it when I was studying asynchronous exceptions. So that's why I'm pointing it out here. So that's the end of the second part. We can take a short break for questions, or we can continue. Yes.
Ivan, there's one question in Discord. They say Ivan mentioned async exceptions can happen in any IO code with heap overflows, stack overflows as an example. But could these two exceptions not be raised in pure code? How would you recover in those cases?
Exceptions raised in pure code, they eventually happen when you evaluate this pure code in IO. So either by using evaluate or by doing some other IO which evaluates it. You can't throw, technically you can throw them in pure code as well, but eventually they will fire when you do IO.
Thanks, I hope that answers good. I don't see any other questions.
Okay. The third part is about multi-threaded daemons. That is applications that run for a long period of time and spawn multiple threads. Normally, they are stopped externally rather than on their own. So firstly, I want to recommend using the async package in such applications. It exports two main primary functions, raise and concurrently. Both of them run two actions in two separate threads. Raise waits for one of them to finish and then forcefully stops the other one, and concurrently waits for both to finish. And importantly, both of these functions propagate exceptions from children thread to the parent thread. So if IO_A throws an exception, IO_B will be stopped and the whole computation will throw an exception. Apart from that, there is this async function, which we mentioned previously. It's not symmetric in A and B, so it stops IO_B action or IO_A action whenever IO_B stops, but it doesn't do anything special when IO_A stops. And async A argument passed to this callback holds thread ID for this thread and something else that is not relevant here. So why should you use this package? It has two advantages if you use it correctly. So firstly, it ensures that no exception is followed. And secondly, it ensures that no thread is leaked. On the following slides, I will give an examples to explain what it means. And in general, I think that the raise and concurrently functions quite well cover the objectives that we typically have in such applications. So we just want to run multiple threads and either wait for all of them to finish or wait for one to finish or use some combination of raise and concurrently function. So here is an example of swallowing an exception. In this artificial example, we create an mvar, which will be used for communication between two threads. Then we run a child thread, which does some useful work, and it puts the result of this work into mvar. In our case, we just throw an exception. In real code, it can be some large code that does a lot of things, but it may eventually throw an exception. And the parent thread waits for reading data from this mvar, and then it can do something else with the contents of this mvar. Now, if I run this code on my machine, it will be stuck for a few seconds, and then it will print this message that is blocked indefinitely in an mvar operation. It happens because the child thread throws an exception and stops before reaching put mvar statement. And the parent thread has no way to know that its child died and will never put anything into mvar. So in a bigger example, in real code, the program would be much bigger and deadlock detection maybe would not work and the program would be stuck forever, or maybe some part of the program would be stuck forever. We can try to fix it using with async function. So we run this child action as the first argument of with async, and then the parent action still tries to read data from mvar, but we will still get the same error in this case because with async doesn't propagate exceptions from the child thread to the parent thread. And if we use concurrently function, there will be no such error because concurrently function propagates exception from this thread here, and the whole computation will fail with divide by 0 immediately. And here is an example of a leaked thread. So here we open a file using withFile function. We pass the file name and open mode. It gives us a handle to this file. And in the callback that we pass here, we use this handle. So we create another thread, which will do something useful for a second. Here we just wait. In reality, we could be reading something, for example. And then it uses the handle to put some data there. And in the parent thread, we just write some data to this handle, and then we exit the callback that we passed to withFile. And then we wait for 2 more seconds. If you run this program, you will get this error that handle is closed. And it happens because when we exit withFile, it already closes the file handle, but the child thread is left running. So it will, after some time, it will try to put a string into this handle, but it's already closed. So in order to fix this behavior, we can use this async, which will stop the child thread as soon as the parent thread stops. So firstly, we will stop this thread, then we will return from this async, and only then the handle will be closed as a result of finishing this file computation. If we don't want to stop the child thread, but instead we want to wait for it to finish, then we can use concurrency function. So now I want to talk about threads that we actually run in our applications. So these threads run actions that normally do not return. For example, such an action can call a library function, for example, run a web server, and it usually doesn't return anything. Or it can run an explicit loop, so it may explicitly call itself recursively. And note that if two actions never return, then race is pretty much equivalent to concurrent. If we have an explicit loop, we need to deal with exceptions somehow, and we have two options. Firstly, we can catch them and continue to the next iteration of the loop. So we can also handle it somehow, for example, log it. But after processing, we will continue to the next iteration, or we can stop the whole application or just the current thread. And in my opinion, there are two criteria which determine the appropriate action. So the first one is severity of the exception that is thrown. And the second one is importance of the thread where this exception is thrown. To determine the action, we need to answer two questions. So firstly, the first question is whether this error is known and transient. So for example, it can be a timeout error when we try to access some web server. In this case, it's likely a transient error, which will be resolved without any action from our side. So we can retry eagerly. We can retry many times until we succeed, or at least until we make many unsuccessful attempts. And if we don't know that, then it makes little sense to retry. So we either do not retry or retry just once, for example. And the second question is whether the thread is vital for correctness of the application. So if we know for sure that without this thread, the application can still work correctly, then we can stop the thread and ideally somehow report that it stopped so that it can be investigated. But if we are not sure that it won't affect correctness, then it seems better to just stop the whole application because application that does nothing is still better than the application that works incorrectly. If we want to retry, in case of an exception, we have some retry policy. So there are two main parameters for it. Firstly, how many times we want to retry on exception. We can have a counter. This counter can be reset on each success. So when action succeeds without an exception, we reset the counter, or it can be monotonic for the whole lifetime of the application. Also, we can retry indefinitely. And the second parameter is how long to wait before retrying. So we can wait for constant time, for linearly growing time, for exponentially growing, and for maybe other function. But I think this you don't need anything except for these patterns because it's likely just a heuristic anyway. And the last thing I want to mention is reporting of exceptions. So it's important to understand that unexpected exceptions require attention, which means that if some exception happens, usually it needs to be investigated and it indicates that something went wrong. If you just log them, most likely they will remain in logs unnoticed until something more serious happens and you start investigating what went wrong, and then you notice that previously you were getting some indicators, but you didn't pay attention to them, and now you need to fix a critical issue. So one way to report exceptions is to do it externally, and usually it should happen anyway. So you should handle the crash of your application. And if it unexpectedly crashes, you should report the fact that it crashed, send logs somewhere so that it will be visible by the developers or maintainers or other people who are responsible for stability of the application. And optionally, you can restart. But again, we have a question whether you are sure that it won't affect correctness of the application. So maybe it crashed because some invariant was broken and you have invalid state. So it's better not to restart without carefully checking what went wrong. And apart from that, you can do reporting from the application itself, which is good, firstly, because you can report non-fatal issues. So if something is already not good, but you don't need to stop the application yet. And secondly, you can have good granularity, so you can report not just that the application crashed, but also report what exactly went wrong. And that's the end of my presentation. So I can answer questions in the special chat.
Thanks a lot, Ivan. That was a really detailed and in-depth talk. I'm sure I'll go back and watch it again.
Okay, thank you, Karsik, and thank you everyone who watched my talk.